So the complexity, this blow up of complexity that happens with all these labels and all your own experiences and how they connect and all that sort of stuff, one can ontologize or fit into a mathematical structure all of these myriad forces. And I think at some point, and this is what I was alluding to before, it starts to crystallize. It starts to, you start to actually be able to see yourself from outside.
Noah is a PhD candidate at the University of Maryland, researching categorical machine learning foundations. Noah founded the Applied Category Theory Seminar at Maryland and believes in foundational reasoning to understand the universe. His work focuses on using category theory to explore knowledge representation and machine learning. Welcome to the James Wiles podcast. All right, welcome to the James Wiles podcast. Today we have Noah Chrein, and we're going to be having a chat about various topics. We've created quite a lengthy list, but let's see how much we get through today, and we can perhaps continue the conversation because there seems to be like a lot of interesting things that we can talk about. There's a wealth of deep insights I'm hoping you can share with us. So maybe you can just give me a bit of background and context for leading into the topic, and just starting off, what have you been up to recently? Like what have you been doing the last couple of weeks since we last chatted?
Yeah, well, thanks for having me on this podcast. I think this is going to be a lot of fun. So over the last 7 years, I've actually been working on a PhD, and that PhD is centered on a theory that started with an intuition that I had a long time ago after reading a paper by David Spivak on ontological logs. So I've been pushing and pushing to formalize a theory for quite a long time. But that journey has looked like so many different things, and we can get into it. So, starting out was just math, and then I think at some point I started to look at my own mind with the math that I was coming up with, and I found some really crazy things that perhaps others may enjoy. So over the last couple of weeks, you asked me, things have really crystallized for me, stepping out of, a bit of a tragic breakup. I started to look at a lot of the knowledge that I had gained psychologically over the past 5 years, the later part of my PhD. And so I started to write a book about it, but I don't want to like give too much away with that because it's in the early stages. But we can talk about that. It could be a good place to
Have you done
start.
some other writing before, or are you just jumping straight into writing a book? Do you do like blog posts and that kind of stuff as well?
Well, I do a lot of writing for myself. I'm not entirely, um, say like, I don't feel a great incentive to share all the time. I'm a very personal person. But over the last couple of years, I've realized that that sort of uh, introversion actually comes from other things, and it's not really a basic part of my personality. So I would like to start writing and blogging um, soon, but I think maybe instead of a blog, I should say I would like to publish books about the
Hmm.
ideas that I and the conversations that I have with others.
Yeah,
So,
that's an interesting concept. Just having this idea of being an introvert. Sometimes there are signs that you're introverted, and then you can self-label yourself as an introvert, and it
mhm.
can justify a lot of your actions, like, oh, I'm just an introvert, or you can feel confident in that label that I don't need to be doing all these extroverted things because that's who you are. You're
Yeah.
an introvert, and I always had that assumption about myself too growing up, because I would often be found sitting by myself doing something like drawing, or just like in my own thoughts, completely fine doing it in isolation.
Mhm.
But in reality, when it came to certain topics, I was the most extroverted person you can find by a huge margin.
Right,
So
right.
these
So how
labels
do you
are,
explain those things is, yeah.
Mm.
I have the same experience. It's like, I can schmooze at a party, and I can tell jokes to people that other people are afraid to even talk to. Yet, I don't want to enter into conversations with strangers and whatnot. And I think that along with certain facets of like ADHD and perhaps other things that prevent you from being your full self,
Mm.
which I should say, actually don't come from a more clinical diagnostic. It's not like a neurological thing. So the introversion, I don't think, is a genetic neurological thing for me, but is actually a manifestation of like a lifetime of self-doubt
Mm.
that you know, very recently, but over the last 5 years have been really overcoming. So,
Okay.
I wonder if you would agree with that sort of thing, that maybe the introversion is actually a protective barrier of some sort.
Yeah, I think these things are very complex, and the more we try to identify the origins of where these traits or statistical anomalies come from, the more we realize it's not an easy identification. Even in just
No.
looking back at how these labels have been classified in the various medical literature over time and how they change almost every couple of years, it's interesting. Like Asperger's has now been removed as a label. So in the past, it was like a very specific thing. Now it's like a non-existent thing, and it's part of a spectrum of what's considered like autism to some
Mhm.
degree. So I mean, we were talking about the human mind, which is probably one of the most complex things we can imagine inside how it interacts with society. Society by itself is a highly complex system. So these things are very difficult to synthesize down to say like you're either autistic or not autistic. So there's some kind of like crossover point. And then once you are autistic, there's also a spectrum. And then it's like either functioning,
Right.
non-functioning. It's too complex to identify. But you had an interesting observation that you said there was like a changing point or like a moment where you said you gained or like you felt like you had received you got ADHD from something.
Well, yeah, let me just step back a little bit because I want to contextualize sort of the approach that I take towards self-analysis. You said, there's all these different factors, all these different labels. If you look at the body of knowledge for psychology and self-help, it's massive. And not all of it is good advice. I mean, there are gurus that go around and they're just kind of BSing. And then there's gurus that are going around and they're saying really profound things. So you have to be able to pick and choose. And the work that I work on, this theory of ontology, I think one can direct this like directly at a self-analysis. So the complexity, this blow up of complexity that happens with all these labels and all your own experiences and how they connect and all that sort of stuff, one can ontologize or fit into a mathematical structure all of these myriad forces. And I think at some point, and this is what I was alluding to before, it starts to crystallize. It starts to you start to actually be able to see yourself from outside. So if you have a good journaling practice or you have a good knowledge representation software that you are constantly dumping in things that you learn to, at some point you can see it from a higher perspective and actually gain knowledge about that.
You can start
But
reflecting on your own thoughts from the past, and it's a way of having access to information that your own mind might have deemed not that important at some point and forgot about, and having this ability to reflect on your own ideas is quite a good idea.
yeah, yeah, and it allows you to group together whatever sort of mathematical structure you can think of. So, for example, algebraic structures or geometric structures can actually be applied to non-mathematical things,
Mm,
like your past experiences
mm,
or feelings.
mm,
And people don't like this idea. They think that it makes your feelings into something dry and like without art. but I don't buy this. I think
I think
it's
it's an
hard,
yeah, it's probably
but
an association to how dry and boring maths is taught at like high school level, and
Mhm, mhm.
then saying like, okay, you're gonna apply that kind of feel like association to my feelings. That's probably not a good
Yeah,
idea.
people get scared of that, especially because they've had bad experiences in
Mm.
math classes.
But I
But
mean, maths
you
is
know,
beautiful when you,
competition.
especially
Yeah.
if you especially look like the more abstract versions of mathematics, they can be quite beautiful, incredible designs.
Hmm.
And the way I like to think about it is it's all patterns at the end of the day, and
Hmm.
patterns exist everywhere and proliferate everything that we do. What's nice with the mathematical patterns is that they are consistent and they have this structure of foundations that build upon one another. So it's not just a squiggly line that I'm drawing in, on a notepad. In the mathematical way of reasoning about it, that squiggly line has very precise um, extensions and ways of connecting to all kinds of other patterns. And
Right.
if you can identify something like an observation or experiment that has this identifiable pattern in mathematics, you can reason about it beyond just that
That's
instantaneous
exactly.
thing.
And you can step out of your attachment to it
Mm,
because there's something very sober about a mathematical representation, so things like trauma, and now I haven't experienced legitimate trauma, but
mm,
smaller versions of trauma, it's very easy to be trapped inside of that trauma.
mm,
But if you can represent it and see it from the outside and hold it in your
mm,
hand in some sense,
mm,
it gives you an opportunity to step outside of it,
mm,
overcome it for
mm,
real. I
mm.
think, at least in my experience. So yeah, that's what that book is going to be about. Is
Okay.
is my journey in that sort of methodology.
It's interesting. It's reminds me a bit of some Buddhist teachings. I don't know if there was
Hmm.
any inspiration from that, perhaps.
Oh yeah,
Okay.
yeah. Well, I think that a lot of Buddhists were like early cybernetics
Okay.
people.
Okay.
From a cybernetics, systems theory perspective, if you read ancient Buddhist texts, it's like, oh, well, they actually kind of saw what
Hmm.
was, they didn't have the language for it, but I think they saw sort of a systems theory approach to the universe. So, yeah.
Yeah, that's interesting. We haven't discussed that much at all. I wasn't aware that you had looked into Buddhism much,
Hmm.
but I've got this thinking of how I think about like what is it like what is the value of what these Buddhists have done? And for me, it seems like this practice of just sitting and thinking and making that like your 9 to 5 for extended periods of time um, means that you've got this like this freedom to exercise your mind to like a very very high degree. And I mean like a lot of it could be wishy-washy, but if enough people do it, there's going to be a few of those people who think very deeply about a specific thing that could reveal knowledge that
Oh, yeah.
was maybe um, on the surface of your mind and was only able to be discovered that like if we think just on the surface of our mind day to day, sitting still and really going deep allows you to maybe look at stuff at a from like deep inside your mind. And
Yeah.
you can only really get that deep if you really meditate hard and for a very long period of time. And perhaps and also getting inspiration from other people's experiences of like
Hmm.
how they were able to do, and these techniques of meditation is quite interesting. And maybe there's a correlation there to maths. It's like these techniques of
Yeah.
identifying patterns, putting different structures together, having like a geometric representation and an algebraic representation, and like
Hmm.
just these exercises of your mind. Maybe there's some kind of relation to the practice of doing mathematics and meditation.
I absolutely think so.
Mm,
And in fact, that's really what the book is about, is a connection
mhm,
between the two. But one of the people that I look up to so much in mathematics is Mike Schulman,
mhm,
and he is one of these guys that has just produced such a wealth of understanding in the field of categorical type theory, homotopy type theory, and higher category theory. And he has a robust meditation practice that he speaks about on his website a little bit, and I've spoke to him a little bit in real life, and that was quite an inspiration for me. I think that I came across meditation before I met him, but then when I saw like, okay, meditation doesn't just put you, on a mountain top with no attachments. It can actually allow you to consolidate your mental forces to do really good mathematical or perhaps business work.
Mm.
And so, it's to each their own what they want out of life.
Mm.
But I think meditation, no matter who you are, can help you, achieve those mental states,
Mm. Yeah,
get
it's
past your ADHD or your trauma to be productive. So,
that's definitely how I find it helpful for me. It's just mental state management. It's like if you're gonna go to the gym and you're gonna work out, it's better to stretch first and like warm up, you know. So if you're gonna be doing a day of hard work with your mind, it's not necessarily the best thing to go from sleeping, drinking a cup of coffee and straight onto emails. You haven't prepared yourself to handle the various like stresses that could just throw you off the edge. So what I find helpful is to have a meditation session in the morning, just to put yourself in a state where small little like disturbances during the day don't just like have this like critical avalanche of neural activity that you
right,
otherwise
right.
wouldn't want, you know.
Yeah, that's a good way to put it, this avalanche of neural activity.
Mm.
I think that that's sort of what the mindfulness sort of movement is. It's like, see when that avalanche is starting.
Mm.
Do enough meditation that you can consistently see when that avalanche is starting and
Mm.
and stop it from
Mm.
becoming from overwhelming you.
Yeah,
Yeah.
even just to identify these things. I mean, these are good practices, and I wanted to actually ask you about ontology itself. So you've mentioned the word, and this is one of these interesting words that I only really came across when I started looking at complexity science in detail, and they normally use this word in conjunction with semantics, ontology, and then I think there's a third one, but there's kind of like these very
Syntax, maybe.
but like the ontological map, the semantic map, something like that. Maybe you
Hmm.
can just give us your definition of what an ontology is.
Yeah, so there's several definitions out there in the world. It's quite an overused word.
Mm.
So I'll say like maybe what the ordinary sort of philosophical meaning of the word is. I first encountered it in philosophy, not in mathematics. And then what I mean specifically in the type of mathematics that I do.
Mm.
So I think that there's several ontologies in different branches of mathematics that mean different things.
Mm.
So yeah, thank you. I'll be quite clear about this.
Mm.
So in philosophy, ontology means like a collection of things that exist. So when you are, saying that something exists, you're saying that it is within the ontology. And in philosophy, there is one ontology. It is the collection of everything that exists. Um, Now, the way that I see ontology is instead of I replace it with a. So an ontology. An ontology to me, and the way that I've read, like David Spivak's work was a high inspiration for me. The way that I read an ontology in his work and also in my work is it is a mathematical structure that acts as a collection of entities that you wish to argue about. So there are billions and billions of examples of ontologies. Uh, the easiest one is like a set, a collection of elements, and there's no relations, no structure. It's just a bag of loose elements. Then you also have a space, and a space has like points and, uh, a notion of nearness for those points. And there's metric spaces, which has a notion of distance. There's algebras, which has a notion of operation, addition, multiplication, division, all these different types of algebras.
So would the
Um,
algebras be in a group, in an ontological group? is it like, are they, how does it work?
So there's various levels, there's hierarchies of ontologies as well.
Mm,
So a set is an ontology. Um, and the collection of sets is an ontology.
mm.
So there are hierarchies of ontologies.
Could you
So
say
all,
then that these are all ontological elements of mathematics?
yeah, I would almost say that
Like maths is an ontology?
yes,
Mm,
yes, math is an ontology of ontologies
mm,
in some way.
mm,
Yeah, and I've had this argument a number of times with mathematicians, and it's really just semantics. It's like, you know, I would call mathematics ontology. The ability to collect things that you're trying to study, contextualize them within that collection, and use the other things that are within that collection to understand the thing that you don't understand. This is a very common theme in mathematics. In fact, I'm not so sure that there's any mathematics that doesn't look like this,
mm.
some way or form.
Would
Uh,
you do you have a feeling that maths is part of a larger ontology that we can even reason about?
yeah, it's quite a scary thought. Yeah,
Okay.
I think that there is a region, like I think that there is a big ontology of ontologies. There's a space for which all collections of things exist.
Mm,
Um, and the subspace, the region for which neural representations, so humans, can reach and reason about, is perhaps not the entire space. So I think that if you want to say maybe mathematics is human ontology,
mm.
whereas ontology could be perhaps bigger, but I don't
And
want to
then
get
would
too.
you put human as a subcategory of neurally capable of being represented?
Yeah, I suppose so. I mean, it's hard to say, right? Because we don't actually know for certain that all of our representations are neurally supported. Like, you know, the idea of a soul or perhaps some quantum effects within the neural networks would be something that is larger than the class of
Mm.
neural representations.
That's the
But
only one I can think of as some kind of quantum effect. Other than that, if you're thinking of it purely classically, then um, is there any
mhm,
evidence so far at all to say that there's anything other than synapses interacting with each other in a classical
I
kind of like way?
I don't know. I'm not a neuroscientist,
Mm.
but I do suspect that it is enough that all conscious events can be encoded in significantly large clusters of synaptic dynamics.
Mm.
Uh, but that is a belief of mine. I have
Mm.
no proof of this.
Yeah.
So anybody watching this, like, this is something that I would like to see proven at the completion of neuroscience. So
Mm.
not now.
Mm.
Yeah.
Mm. That's very interesting. So you just mentioned something as you were explaining ontologies, and you threw in the word semantics, and you're saying that these are semantics. And is there a clear relationship between the semantics and the ontologies? Like, how are these things related?
Yeah, so there's the word semantics in category theory, which to my mind, it's not well defined. It's a sort of one of these words that the people at the edge use to mean something, and the community kind of knows what it means, but there's no definition of semantics.
Interesting.
The way that I see
Isn't that
semantics,
ironic in a
yeah,
way?
yeah. No, seriously. Well, it's not complete. Like, the field is definitely not complete.
Mm-hmm.
So I see semantics as an interaction between syntax and semantics, and I think that's how other people see it as well.
Isn't it a
So
self-reference?
yeah, so semantics refers to the mathematical structure, and syntax refers to the formal language by which you specify that mathematical structure. So a topological space in the fields, in the field of category theory would be semantics. It's, the sort of structure.
Mm-hmm.
Whereas, like homotopy type theory, which is how you type out on a computer a topological space in some sense would be the syntax. So,
Mm.
the language that you use to describe a structure is the syntax, and the structure itself is the semantics.
Mm.
At least that's how I see it. Again, these
Mm.
things are not well defined.
So when you go to a Wikipedia article, there's the semantics, or if the way I've seen it being used just day to day is like describing what a word means, or like the origin of a
Mhm.
word.
Mhm.
Yeah.
Yeah, so I think probably what they take from that is like the word means,
Okay.
So semantics is like the real meaning of it, and syntax is like the way that you describe it using, symbols, formal symbols.
And then just another question on the ontology picture now. So I've got this kind of like visual representation in my mind. One thing that would be interesting for me to figure out from you is that the difference between a hierarchy of collections and some kind of more like hyper edged sort of relationships.
Mm.
And a simple example would be we mentioned taking notes earlier. If you go into a normal note taking app, you kind of have folders and you have documents, and then you can have like maybe the document has so you have like multiple hierarchies of directories and folders, and you can have one folder with documents and other folders. But everything that exists has to belong to a higher order in some way.
Mm-hmm.
But there are very many different knowledge representations where that's not the case. And there's these other types of knowledge networks where it's almost like a graph, and things are connected in multiple ways to multiple different things. So in ontologies, can ontologies like overlap?
Yeah, ontologies can overlap. I suppose you would have to say that they overlap.
Mm.
But okay, so going back to your folders versus this other knowledge representation system. So the folders are quite clearly hierarchical,
Mm.
but it's not so clear how this knowledge graph, is hierarchical. And it's not actually
Mm.
on the flat level, like, working with a knowledge graph itself, it's not hierarchical. However, the meta mathematics that surround that graph
Mm.
is hierarchical. So to define what a graph is, you say, oh, it has nodes and edges, right?
Mm.
And so now there's a whole collection of things with nodes and edges.
Mm.
Your knowledge graph is one of these collections of nodes and edges.
Mm.
And so all of these collections of nodes and edges sits within the collection of graphs.
Mm.
So when I'm talking about meta mathematics, any system, you can step outside of that system and provide um, let's say, structural specification of that system, for which all the systems that satisfy that specification are within this hierarchy. So, yeah, this is meta mathematics. So
Mm.
anything that's like direct is not going to seem hierarchical, but there's a way to step above it and, collect all the things that you are talking about, and then
That's
it is hierarchical.
interesting. And
Yeah.
if you are able to step out of it and clearly identify that it is a graph, and graph has the following attributes and operations maybe, or things you can do to it, then you can start reasoning about the information of the graph maybe once you're able to step out at a higher perspective, I guess.
Absolutely.
Mm.
Yeah. Yeah. For example, if you have your favorite shape in a graph, like perhaps a triangle, may tell you about like associations within a graph.
Mm.
And so if you step out into this level of collections of graphs, you could then look at perhaps embedding this triangle into all the different graphs. And
Mm.
then what you would see is not just the graph that you have, but the associations within that graph that you
Mm.
have. So
So,
stepping out an ontological level
mm.
allows you to reason in context with all the other structures that are like the structure you're using.
And that's
Um,
interesting, and specifically attaching an ID to it. So having like what the way I'm using the word, I could be using it wrong, but like a semantics of saying like, okay, this is a graph. It's not just a no-name ontological shape. Having specific semantics with how to reason about it gives it structure, kind of like a broader structure. And I was wondering if going back to what you mentioned, if you twist, or if you turn those ideas and concepts onto oneself and start thinking about like you as a person, how you operate in society and that kind of stuff, is that what you meant by being able to reflect on your identity and who you are as a person, by saying like, okay, I can step out of who I am as like James and say like, oh, James is a person. Oh, interesting. Okay, so what do people do? How do people operate? And then you can say like, okay, well, I know what people do. I have an idea of like humans and all that kind of stuff. But it requires you to first identify that and,
Yeah.
you know.
Yeah,
Mm,
exactly.
mm,
Exactly. And I think that a lot of people are quite resistant to this because, they say, "Oh, I have an identity." And to an extent that's true, but to another extent it's not true.
mm,
You actually belong to the human race, and perhaps you have unconscious forces that everyone has that you're ignoring. And
mm,
so if you step out of your like rigid identity and you see, okay, well, evolutionary psychology dictates that this, that, or the other thing's going to happen. You know, for example, among mathematicians, there is a large denial of sexual desire, right? So, you know,
do you mean
people
mathematicians
deny,
themselves?
yeah,
Okay.
mathematicians themselves will
Okay.
will deny that this exists.
Interesting.
And there is a large body of evolutionary psychology that says that if you ignore this, you're going to be in pain. And now there are
Mm,
people who are truly asexual. I'm not
mm,
saying that that's not true, and you have to analyze that for yourself.
mm,
But to deny it for a mathematical principle
mm,
actually like ends up harming you.
mm,
So you have to be able to step out of your identity, is what I'm trying to say,
mm,
even if it's uncomfortable,
mm.
and see
And
it within the context of the other humans that you're a part of. Yeah.
and you were there specific situations or concepts that you yourself, having identified mathematical patterns, could apply to yourself and reason about?
Um, Sorry, wait, can you ask
So
that
in other
again?
words, knowing a lot about these mathematical patterns, was there any specific examples of some mathematics that you applied to reason about yourself as Noah?
Yeah, definitely. I think that a knowledge of like differential structures
Mm-hmm.
and to think that for that perhaps like the movement of uh, neural clusters within your brain. So activation sends one neuron to another,
Mm-hmm.
one activated neuron to another activated neuron, but like within large groups, this is like clusters of neurons.
Mm-hmm.
And I have this belief, again, I'm not a neuroscientist, I don't have proof of this, that concepts can be held within those dynamic neural clusters,
Mm-hmm.
and those dynamic neural clusters would follow the laws of physics,
Mm-hmm.
conservation of energy, but also, locality and causation, and, not even necessarily like relativistic, like just very standard, this happens, so the next thing happens,
Mm-hmm.
and there's an inertia of these movements of neural clusters. One can visualize directing their attention, which is these neural clusters, towards the source of emotion
Mm-hmm.
that is perhaps bothering you.
Mm-hmm.
So you say have some unspoken pain or, perhaps unspoken pleasure, whatever it is,
Mm-hmm.
like that you want to um, make representable, make manifest, put your attention on in a way that makes it something real. You can use like the idea of like this mass of neural clusters following a differential calculus and move that towards the direction, like almost like a gradient descent,
Mm-hmm.
the direction of the source of that emotion.
Mm-hmm.
And I have found like I don't have like neuroscience proof of this, but I certainly have like psychological results of doing this.
Okay, interesting.
Yeah.
That seems
Mhm.
like a combination of having a visual representation that you can hold in your mind and work with as something that you're trying to do when you're thinking about these things, as well as some intuitions that are gained from real mathematical advances, like for example in machine learning, where you have this concept of local minima and error reduction, and how how you can be very efficient with that using linear regression and saying, okay, at this point, maybe does this feel like this is the source of some kind of pain for me? Like how far off am I? And it's like, not really. Then you think about something else. Maybe you think back to like
Yeah.
another memory that's closer to it, and then you can identify, oh, there's some emotion welling up. So the error rate is low. It's like it's
Yeah.
getting to some kind of like local uh local like closeness to the source of some kind of fitting of my mind of what's happening to me.
Right. Yeah,
Mm,
yeah,
mm,
exactly.
mm,
And this pairs quite well with the mathematics that I'm developing. I think the main point of my thesis is this notion of the ontological step.
okay.
So the step where you start at something that you're studying, and then you create a mathematical structure to house that thing you're studying
Mm-hmm,
so that you can use the context around it to understand it. And
mm,
so when it comes to emotion, it's like you're experiencing sadness.
mm,
So take the ontological step, create the mathematical structure that houses that emotion,
mm,
which is now a search space that
mm,
you can then, move within to study that emotion.
mm,
And I found it very effective,
mm,
not just in meditation, but like in proving mathematical statements. I mean, if you look at a lot of mathematical proofs, a lot of times it's like you're trying to show that A equals B. And so what you do is you create large A for which A and B are in this,
mm,
and then I don't know, find some way to prove that A is equal to B. There's
mm,
definitely a better example than this, but this tends to be how it goes.
mm, mm. Yeah, so what this is making me think of is a situation where you can have a word for something, and just being able to identify it gives you a lot of power. And the example that you used there of like sadness is very interesting, because if we did not have the word for sadness, and a lot of people teaching you, growing up, like, oh, what you feeling now, are you sad, or like you're
Mm.
crying, you've got like some kind of external indicators. But in lieu of that, and in lieu of a word and kind of like this societal education, or the societal technology, or maybe just language technology to identify those things, like the power of semantics,
Mhm.
then it would be pretty difficult for you to self-identify the difference potentially between anger and sadness. You just
Yeah.
feel upset. There's some kind of like emotional instability, and you wouldn't even be able to put a label on it. You'll just be like, oh, why can't I sit still? Like what's going on with me? You don't know if you're sad or upset or hungry. So
Yeah.
just having a clear identification for something gives you a lot of power.
Yeah,
Mm,
absolutely. I
mm,
think that that's a fantastic point, and that happens, in mathematics as well. Like, there's this notion of witnessing as
mm,
opposed to proving.
mm,
Um, and this is one of the basic notions in homotopy type theory, but also
mm,
in higher category theory, is that like, we have these operations that we can prove, or we could have a piece of data that witnesses, gives a label to the existence of this operation having already been done. So if you want to compose, say, two functions, the way that you do it in ordinary categories is you do F plug into B,
mm.
F plug into G, sorry. So F
Plug
of
in.
G.
Okay. What does that symbol
Yeah,
look like? Plug in.
the circle compose
Okay.
function compose. So like you want to compose two functions, f of g.
Mm-hmm.
It's the composition of those functions.
Mm-hmm.
In higher category theory, we have a witness for those compositions. So as opposed to computing f of g, we have like a piece of data that has already done that computation and and holds it within a label that looks like a shape.
Very
Um,
interesting. And but this is not a proof. It's just it's like evidence maybe, or it's like some kind of
yeah,
yeah. Okay.
So there's a concept in math called the Curry-Howard correspondence.
Mm-hmm.
And it's a correspondence between I mean it's stated in terms of proofs and programs, but I guess I think of it in terms of proofs and data. So it's either we prove things as mathematicians,
Mm-hmm.
or we have data that's supplied with the things that we're trying to prove things about that supply that proof.
And
So,
what if you come across data that's contradictory?
well, I mean, you have to set up your system correctly.
Okay.
There's always like levels of meta that end up screwing you up, but
So are you saying
perhaps,
it's more that like data can exist? The fact that these things produce data which is the result of those compositions is the witness that those compositions are valid or something. Or is it like, does it have to do with the nature of the data perhaps, or something like that, that makes it a valid um, statement, a valid mathematical statement, or not necessarily?
um, yeah, not necessarily. You can assert these things. They don't necessarily need to be true from some other. So this is probably a better example for viewers, and also because I seem to be struggling with explaining this.
Okay.
So like in homotopy type theory, right? One of the main um, advances from ordinary type theory is the replacement of judgmental equality, like
Mm-hmm.
A equals B,
Mm-hmm.
with like a collection of equality judgments. So a collection of statements that A equals B. So these are like you could think of different proofs that A equals B, but you've
Mm-hmm.
already collected them beforehand.
Mm-hmm.
Uh, and so each of these equalities from A equals B, which you can think of as like different paths in a space.
Mm-hmm.
You have a point A and you have a point B, and you can get from A to B with different paths.
Mm-hmm.
Um, since these are now data,
Mm-hmm.
you can now talk about equalities between the equalities.
Mm-hmm.
Um, this allows you to like deform proofs of A equals B into other proofs of A equals B. These are two equivalent proofs, for example. Um, so when you set up one of these spaces, this is all done like a priori.
Mm-hmm.
You at the beginning, at the outset, you're telling me, all the ways that A is equal to B.
Mm-hmm.
Uh,
So you've got the
whereas,
data. It's like an observation. You've collected a series of facts, and now you're
yeah,
yeah, yeah.
yeah,
Interesting.
exactly.
Okay. So
Yeah.
so what you're saying, yeah. I mean, I've only realized came across this concept of a witness recently in trying to prove a to construct a proof, and somebody said like, oh, like once you've done that, that's a witness, and then you can like use that to reason about it. So
Yes.
it's definitely interesting. What's interesting about these things is that the words that were chosen, like witness, is kind of similar to like a witness observes. And you have this idea of like there is an observation, and the
Mhm.
observation leads credence to the fact that it exists. But then it
Yes.
also has this feeling in the physics world of saying like the observation of the thing is almost like what makes it real. These are my
Mhm.
words, but it's
No, I
how
agree with you.
I like to reason just to myself in terms of the difference between quantum mechanics and classical mechanics, I guess, is that in quantum you have the state of like multiple things legitimately existing simultaneously in potentially contradictory ways. And the thing that resolves it is an observation. And
Mm.
the fact that it has not been observed is what puts it into multiple states.
Mhm.
So there's, yeah, we
Yeah,
can get into that.
there's a
Yeah.
slight, I think there's a slight difference between like wave function collapsing,
Mm-hmm.
observing,
Okay.
and creating like data to house a witness of things. Because, you know, I think in the before collapsing, superposition of several different wave functions, each of these wave functions can be labeled. And I would
Mm-hmm.
say that that is a witness for the wave functions
Mm.
that you're
But is that not just encompassing the quantum states in an observable already collapsed like identification? Like, what if you have
Maybe,
the
yeah.
quantum state of multiple quantum states? Then you just go back to the fact that this is not yet observed, right?
Yeah, yeah. I don't necessarily know how to argue about this, but yeah.
Okay. Yeah, it's interesting for
Um,
me because it was a thought experiment I was doing to figure out how to solve like Bell's inequality theorem.
mhm,
And the idea with that, just for those that are interested, is that you have two particles that are quantum entangled, and they'll send to two different people, Alice and Bob. And then there's a game that they play where they have to try to guess what the other person's quantum state of their particle is based on them observing their particle and then trying to guess what the other particle is. And basically, your highest probability game, the way you can win most of the time, um, or let me rephrase it, particles that are in a quantum entangled state allows you to have a greater than 50-50 probability chance of both of you guessing correctly what the other person had. So
mhm.
there's a way to leverage the fact that these particles are quantum entangled. So in thinking about this, one of the ways I reason about it is the fact that the particles themselves can be identified as particles and that they are moving around in like a classical way, but the state inside it has not been observed yet. And that's what makes it a quantum state. So you have the particle, but the state's at a higher level. And then, I mean, this is kind of like where I start thinking a little bit maybe beyond the realm of what's scientifically valid, but then you can kind of say like, okay, well, potentially the universe could be thought of this way, where the observable universe has a subset of the observable universe, which is the observed universe. So this is what you can define as, consciousness, or any one human, the various things that they have observed, and that's housed within an observable set. And outside of that is kind of like the realm of all possibilities. And that is kind of like the quantum state. And as the universe, or as the set of observed things increases or changes over time, so the realm of possibilities is collapsing into this like observable space. So that's how I use this idea of like quantum mechanics and classical mechanics to reason about bigger concepts. Not at all scientifically valid, but it's like a fun thought experiment to take one realm of concepts and apply it to try to understand about physics. And then the last thing I'll add to that is you can even go like, that's kind of like the limit of where this idea or this concept goes, is like the laws of physics. But then you can bring it down back to a very human level, and you can say that if you're a hunter in the savannah and you're like trying to hunt some prey, and you're in the bush, and now you're trying to identify if this animal that you're chasing, let's call it a buck, is behind a rock or a tree, and it's behind. There's definitely a buck. You saw that there's a buck, so you've observed there's a probability of there being a buck somewhere here, but now it could be behind the tree and it could be behind the rock. So in view of literally zero other evidence, how can you say that they're not to some degree behind both at the same time? Do you know what I mean? Like there's
Well, yeah,
almost, right?
superposition principle.
Yeah.
Yeah.
So it's like they're in a superposition until the point that they're not. And
Mhm.
although this is just a kind of like a play of words, you're saying that the buck is in a superposition because you haven't actually like thrown the spear or created some kind of like observational data to determine if where it actually is. Um, to me, it sounds like that's a perfectly reasonable way to think about the world and to operate in the world, is to say like these are a realm of possibilities. They all exist at the same time, and it's only once you actually create some action or activity or observation that it collapses into like a physical manifestation.
Hmm. Hmm. Yeah. Um, well, while you're saying this, I was thinking a lot about the difference between reality and models of reality.
Mm-hmm.
So, you know, whether or not that buck is actually behind the rock is not necessarily what we're able to hold.
Mm-hmm.
Like I'm not actually holding in my mind the actual buck. I'm
Mm.
holding my representation of the buck being behind and the rock and the space of the rock. So I guess I want to bring it back to what I know, which
Mm.
is like the difference between the word the and a for
Mm.
ontology. And it is really a difference between um, a model for the universe, which may be, whatever quantum physics sort of superposition stuff you want, or classical mechanics or relativistic mechanics, Hamiltonian, anything, right? So any model of the world, it would be, I think, irresponsible to say that that is the world. And a lot of physicists say that, this is the way things are, right? And I resist that. I say, like, this is our best model or our not even best, our current model
A model.
for
Yeah.
a model
Mm.
for the way things are. And I think that that sort of liberates the mathematician quite a bit for more creative pursuits, because it's like, if you can have, say, this situation where the buck is behind one of these rocks and you're guessing 50-50, there's a superposition of states. There's also the model where you have kept track of the footprints of the buck.
Mm.
And, so if you see footprints next to one of the rocks, this is
Mm.
extra structure that you're
Mm.
adding to the system.
Mm.
So if you're adding those footprints to the model, then you get a different probability
Mm.
distribution. Footprints next to one rock and not next to the other, like, okay, there's a lot of evidence, but those footprints could have come from a different time or a
Mm.
different animal. So, there are like I hesitate to say infinitely many because that's not even big enough, but there are infinitely many models of this situation of the buck being behind one rock or the other. No matter what, that's not reality. These are
Mm.
just different mathematical structures that operate as models for
Mm.
reality.
And those
So
models presumably are sitting inside your mind. And these are some kind of patterns of neurological activity that are representative of the observations that you're making, right?
right, right. So yeah, if we got to be honest about this. Like, mathematicians like to talk about mathematical structures existing on paper, or perhaps even they exist in the zeitgeist, but like they're really existing in the mind of the mathematician that is
Mm.
thinking about them at any moment.
Mm.
So I'm not a Platonic idealist. I don't think a square exists, but I
Mm-hmm.
do think that one can hold a representation of a square.
Mm.
Um, and this gets into perhaps a different topic. I don't know how much time we have
Oh no, we can go.
here
Yeah.
about the like natural emergence of mathematical structures um, through neural representations.
Mm. Yeah, that'll
Um,
be
you know,
interesting. Yeah.
how did we end up at, say, category theory, or even, less abstract things like how do we end up at 1 + 1 = 2?
Mm.
Um, Starting from, you know, sea slugs that have a little bit of fungus on their head
Mm.
and evolving all the way up through reptiles and primates. There's it's not like, I mean, I don't necessarily believe in a personified God. Maybe the
Mm.
universe is God, but I don't necessarily think there was a moment that God reached down and said, okay, 1 + 1 = 2.
Mm-hmm.
I think that it emerged from evolution.
Mm-hmm.
Evolution molded neural representations to hold the idea 1 + 1 = 2.
Mm-hmm.
Uh, so, what are your thoughts on that sort of thing, that emergence?
Yeah,
Of
so there's different ways to think about it, and I've heard people describe this in the past as like, is mathematics discovered or created?
mm,
And it's an interesting thought. I think if you were to use the sea slug example, over many evolutionary cycles, the fact that two other sea slugs around you like fought and there was only one survivor, this idea of like two and one became very physically real. And that could have physical effects on you even before there was the neural pathways with which to represent that abstract concept. So in that example, as an outside observer watching the sea slugs in a fish tank, for example, there's many ways that you can see the identification of a fish slug and the concept of one and two manifest in the existence of what happens to that sea slug, or the lineage of sea slugs as a pattern of life form. And to the degree that maybe any particular sea slug ignores the reality of 2 plus 2 equals 4, 1 plus 1 equals 2, and has some kind of decision in whatever decision it makes in its environment that it thinks 2 plus 2 equals 3, and that was a mistake that that ends up in that sea slug perishing. That means that whatever it did, the mathematics caused it to stop being. And maybe this like environmental concept or this physical law of mathematics is constraining the set of potential organisms that exist to only allow those to have some kind of ability to experience truth more, like, and that was actually a concept I wanted to ask you about. But there's almost like there's like the truth of 1 plus 1 equals 2 affecting what happens to the organism, beyond the idea of that organism even appreciating what truth is potentially.
So you think that 1 plus 1 equals 2 is some fundamental truth of the universe that then neural representations evolved to create an abstract representation of?
I'm just mentioning that as a possibility. Yeah, I don't have any specific beliefs about this.
No, me neither. I mean, I don't know how one would go about. This is like an age-old argument. Do the natural numbers actually exist, or are they just, tools that we came up with?
And even a more practical question is, to the degree that we experience them as true and they exist, what's the point of asking the question? So in other words, if our experience of it is that they exist, then why should we bother asking if they exist beyond that?
Well, I mean, there's plenty of, say, better models for phenomena than discrete, natural numbers. So, at some point we had to ask ourselves, if, what is a better model for this specific phenomena? But you brought up an example of, like, say, two sea slugs, they fight, and then now there's only one sea slug, but that's not the full systems like view of this, because two sea slugs, it's not really two sea slugs, it's two like distinct jumbles of atoms and compounds that are interacting with each other. And when is it a half a sea slug? When is it a quarter of a sea slug? Maybe the number one sea slug is not necessarily the way to, like, it's not accurate enough. It's like this exact collection of atoms and dynamics of atoms. Like, to say sea slug, that's a very human, we love the natural numbers, so of course it looks like there's two sea slugs, but really there's like this giant collection of atoms operating in a system, and perhaps there is no one entity. So
yeah. So the thing is, to the degree that you as a third, let's say the witness sea slug, like watching this fight, to the degree that you don't appreciate the fact that that is one and that is another one, and that together they were two or something like that, means that so to the degree that you don't appreciate those realities is going to jeopardize your survival. I think that's what I'm getting at. So from one perspective, you could say the concept of there being a one and a two and so on exists, and the degree to which we can appreciate that as truth helps our survival, and evolutionarily this becomes like an ingrained concept. The other way to think about it is potentially that, like what you said, these are just models of knowledge representation, and you can slice it many different ways, in discrete and continuous ways, and they have different advantages in different contexts to reason about stuff. And the vocabulary with which you're able to describe things, if it's richer, it means you can describe more things, and your knowledge representation can be a lot more fine-grained, and your ability to make decisions in the world and survive and continue your pattern of decision making is improved. And you could, in that example, say that nothing exists and everything is just knowledge representation. You can slice and dice it however you want. All that matters is the quality, and there's not an objective, solid truth. And then you go towards some people's claims that there is a ground state at which there is a specific knowledge representation that you cannot go lower on. And then it might just be that that is like a very simple rule that's just extremely, that it's a very simple rule that run at a larger scale creates very complex emergent phenomena, which could be like the whole of the universe. But there is a knowledge representation that exists at the basis that you can point to and say, okay, take that very simple model and just extrapolate it, and you will get all of the phenomena that is possible of being observed.
Right. So yeah, two thoughts. So the first thought, yeah, that's a great way to look at this. It's not so much what model is the base truth. Like, okay, yeah, perhaps there is no 1 and 2 at base truth. However, the having the model of 1 and 2, by which one can house in a small neural network, the 1 and 2, like being able to hold and wield that representation of the world increases your survival chance. So the slug understanding that there's another slug, there's one other slug, is better than the slug that doesn't have that model, or the slug that has the model of, oh, here's this blurry mass of things, I don't know what to call it. That slug is probably not going to survive. But the slug that has, because we have a limited amount of attention, the ability to say, here's one other slug, had the better abilities to survive. So it's not so much that 1 and 2 and the natural numbers are true. It's that the model, like having that model, helps you to survive better. So perhaps that's what I'm getting at here, that like mathematics, so the basic elements of mathematics, like object and relation, these ideas of object and relation are things that were better models of the world than things that didn't have them. So, object and relation, that's like key to category theory. So I feel as though category theory and all other math, every other piece of math, is emergent from evolutionary forces on neural networks.
It sounds like a synapse and an activation, like you have the object and a relation. And is it maybe and the thought that comes to my mind is that is the effectiveness of these models, let's say category theory, at explaining things that we observe, not based on the fact that all our observations ultimately must be held within our neural net, and that because the neural net itself is objects with relations, that could be a fundamentally accurate representation regardless of what might exist outside of our neural net, because that's an unreasonable space. There's nothing that we can reason about there. All we have is what we are able to reason about, which happens to be a neural net, which might be quantum, but that's another story.
But so I agree with this. I mean, there's two things that are required for evolution. There's the random chance that it occurs, and then there's it makes survival easier. So if you
there's also selection, which is the
well, I think that's selection. So the second one is selection. There's the chance that it occurs and the selection.
So there's actions you can take.
So
I was more referring to sexual selection, which is the other half of Darwin's.
I'm talking about generalized selection, like the fact that I was able to see a piece of food selected my caused me to survive, and that was nature selecting my survival.
Yeah, I mean,
Is
what I'm trying to think about here is just an appreciation that I've gained over time for not just thinking about in terms of survival, but thinking also on the other half of that, which is the reproduction. And the
mm,
reproduction is almost always a selective process. It's not, it's very seldomly by mistake. Whereas
yeah,
survival, there's like this randomness that comes into play. Um, how you decide what genetics get carried forward is not only about what survives. There also has to be a reproductive side. So I just wanted to bring that in as a additional element to reason about within your model.
right, yeah. So you're when you say selection, you're saying sexual
Yeah.
selection. You're
Mm.
But when I say selection, I mean like nature doing selection. Like nature
Okay. The environment selecting
chooses.
upon you.
Yeah, yeah,
Okay.
yeah.
Okay.
So,
Okay.
like in some weird, very esoteric sense, dropping a ball and having it fall to the ground, nature is selecting that ball falls to the ground. It is the outcome of whatever actions were happening is selection.
So you would put
Um,
the laws of physics into the category of nature.
Yeah,
Mm.
yeah, yeah. And also like the mechanism of selection is the laws of physics. Um, I think that's how I'm
You
saying
you
selection.
might need to break that one down. So
Mhm.
how would the laws of physics be doing selection?
So think of it this way, like, so I should say that like a lot of these ideas come from this guy Lee Cronin,
Mm.
um, and he talks about oh, I forgot what he called it. Um, but he has this sort of view of, say, chemistry that brings into the like the conversation this notion of selection. So, why is it that a that carbon atoms will bond together in a helix as opposed to like say some weird other shape, right?
Mm-hmm.
It's because the electron repulsion forces are minimized in that helix shape and not in this crazy jumble of other shapes,
Mm-hmm.
right? If you had a crazy jumble of carbon atoms, somehow they would end up pushing each other away and forming helixes or chains or whatever organic
So wouldn't
compounds.
that be an example of an inevitability?
So this is what I mean when I say like physics selects
Mm.
the shape of things.
Okay.
So
Okay.
the laws of physics, the repulsion
Mm.
due to the electron forces,
Mm.
um,
Selects the
select,
potential shapes that it wants to have exist.
yeah,
Mm.
and shape in my view is not just like the shape of carbons, but like like any outcome ever is the
Mm.
shape of the world or
Mm.
whatever it
Mm.
is.
Mm. Mm.
So that's what I mean by selection.
Mm.
Um, Right. So in my view, evolution has two things. The chance that something occurs
Mm.
and then the selection of that thing.
Okay, and that could be at a physics level. The selection could be, okay, you're just unfortunate, to fall off a cliff, and physics is going to select that that's a non-survivable event. Um,
Mm-hmm.
so what would be the difference there is if you think it's a good idea to try to jump off the cliff and see if you can survive or not, and then having physics select that that's a negative outcome versus the cliff collapsing and by chance, even though it was not your intention, you ended up falling down the cliff.
Well, so there's like um single selection, and I guess there's like selection that's integrated over an entire species.
Mm-hmm.
So, the cliff falling and you dying and you didn't do anything wrong, you just
Mm.
were standing at the wrong place at the wrong time. Yeah, that's selection. Like
So then would
you
that not
lost.
be the difference between? So I'm trying to differentiate between the difference between selection and random events occurring.
Hmm.
So maybe is there a different example you can paint the specific difference there,
The
like
difference
chance
between
events? Because you mentioned, yeah,
So
that
yeah,
there's
so
two.
what what,
Yeah.
what I'm trying to say is that like, what is possible to have been to undergo selection.
Mm-hmm.
So like, okay, of course, a monkey that's handed a gun
Hmm.
is going to have a better time surviving if they know how to use a gun
Okay.
than a monkey that isn't handed a gun.
Okay.
However, the possibility of that gun coming down from, whatever, and put into the hands of a monkey and the monkey knowing how to use it, that is probably not going to occur. What's
Mm,
more likely to occur is that a monkey, say, tastes a new kind of banana, and that banana has a higher caloric, thing. And so, that monkey says, oh, hey, let's go start eating these bananas instead of those bananas. And then this tribe survived, but that tribe doesn't, whatever.
mm,
So there's the possibility for those bananas to exist.
mm,
And then there's the selection, which is the higher nutrition of those bananas.
mm,
But like, so a gun falling into a prehistoric monkey's hand, like that's not possible, really.
mm.
So that's like the first layer of evolution is what is actually possible to happen. And then once it happens, over random occurrences and a bunch of times, how does it play out? And that's the selection side of it.
Yeah, I think what's interesting there is that touches on the source of random events
Hmm.
and the source of um, unpredictable, let's say, things happening. Because you could say if you understood physics to a high enough degree, you could predict all of its selections. But then you're saying there's another thing that prevents you from doing that, which is the probabilities and the chances of random things happening.
Hmm.
So it would just be interesting to reason about the fact that maybe physics produces, like all of randomness comes from physics. And is there perhaps a model of physics that could account for all randomness and that you could actually say randomness is, um, if you had the best possible model of physics, that and assuming that there is a ground model of physics, could that reduce all of randomness to just um, requiring enough computation to calculate the result or the prediction?
Maybe. So this is branching off into a different topic. Because maybe I just wanted to, so I do actually want to answer that question.
Mm-hmm.
That has some implications as to other things that I've thought about before.
Mm-hmm.
But I just want to go back to what I was saying about like, the emergence of mathematics through neural representation. And I was talking about, what does like evolution being sort of two things, what is capable of existing, and then selection amongst the things that are
Mm-hmm.
capable of existing.
Mm-hmm.
And so, the random thing that started neural networks, at least in the like view of origins of life that we have, is that sea slugs brushed up against underwater fungus, and
Mm-hmm.
this underwater fungus, caused the sea slugs to move to the left a little bit more. And
Mm-hmm.
over a billion years, it turns out that moving to the left or to the right a little bit more was better. And then we started integrating, those neurons, which were made out of fungus,
Mm.
into like um, things that evolved into brains that we have today.
Interesting.
Um, and you were saying that object and relation is very synaptic, right?
Mm.
So, we have this really general form of mathematics for which almost all mathematics fits into called category theory.
Mm.
And the basics of category theory is objects and morphisms or
Mm.
relation, objects and relations, really. So, it's like the sea slug was handed the gun
Mm.
by um
Fate.
so handed neurons by the mere chance of these fungus being close to them,
Mm.
and so from that chance then selection occurred.
Mm.
So it's in some way it feels like object and relation, the fundamental like understanding of object and relations started with those sea slugs.
Mm.
And it only became manifest, once we have enough objects and relations that we can house abstract representations and say, oh, this is an object and this is a relation.
That
Yeah.
that's a very interesting story. I think what I would like to see if I can let's see if I can pose this as a question instead of a dialectic.
Mm.
So, would you what do you think about the potential for the fact that this fungus had this pattern of being able to represent knowledge in a specific way, let's call it with objects and relations. The fact that they were objects and relations, there could have been any other type of pattern potentially, that was somehow more accurate a representation of underlying physics,
Hmm.
which helped it to survive.
Yeah. Yeah. I mean, like geodesics, the notion of path, like, shortest path between 2 points is quite a powerful concept in physics. Like you can almost do everything using geodesics if you're clever enough.
Mm,
Uh, and so, yeah, like sending a signal from point A to point B is utilizing sort of a more fundamental notion of geodesic that perhaps exists in physics without the human mind.
mm,
Uh, so, I mean, we like to say that relativity is, that the universe operates in the sort of space-time relativity type thing.
mm,
But it is our model for it, but it's quite accurate.
mm,
So there's got to be, I don't know if there has to be, but it feels like there is something real that we are modeling.
mm,
So I would say that we have to be careful. Everything that we've ever constructed, so relativity included, is a model for reality.
mm,
But what is reality? Um, and were the fungus also modeling reality at a really good survival level?
mm.
So yeah.
Yeah, it's interesting, and you can even reason about potentially just the fact that it allowed for greater amount of complexity, and that it could have been any other pattern is
Mm.
also interesting if you think of it from a like an adaptive, dynamical adaptive kind of
Right.
like point. Yeah,
Yeah, yeah,
mm,
right.
yeah,
It's hard to imagine other patterns because we evolved from that one.
yeah.
But yeah, been some crazy other patterns.
And there's just an idea that you remind me of that I'd like to run by you, and this was this concept of how looking at it in a specific way, one could say that the discovery of mathematics has physical outcomes on reality. So,
Mhm.
if you think about like Pythagorean theorem, once we discovered Pythagoras' theorem, there seem to be more triangularly powered objects that have emerged in society.
Mhm.
And it feels like the creation of some kind of consistent reality in a highly abstract mathematical space, which is just, neural activities. And to some degree, those neural activities interacting with like the writings of other people, the drawings of other people, even inspired by nature, or interactions with some kind of fungus you found in a forest. But the point is that these were not manifest yet; these were just like ideas and concepts. But the ideas and concepts have physical manifestations that occur. I just wanted to run that idea by you and what you thought of that.
Um, well, so I think that um I'm sort of caught in between perhaps two meanings that you might have. Are you talking about sort of this phenomena where once you know things, once you're a hammer, everything looks like a nail? So like once you know about triangles, everything looks like it's triangles, or
No, more a case of, in practical terms, once we understood how Pythagoras theorem works, or the benefits of like right angles, or being able to judge about like the weight of things and then using mathematics to determine how high a tower can go. Once we firmly established the concrete mathematical proof that you could go to like you could build higher towers started emerging.
Mhm.
So it's just an
Right.
interesting, yeah.
So yeah, I think we had this conversation last time where, it's like, um, yeah, our neural representations, which up throughout history, we've sort of said we're not real. We've
Mm,
said that the mental was different from the physical.
mm.
But clearly, yeah, understanding Pythagorean theorem emerged skyscrapers. Um, so,
It's an
but
interesting
it
thought experiment to think of it the other way. You know, perhaps there is a physical action that these profound pattern discoveries or creations has on the physical world, even though it's all just in your mind.
Well, yeah, so yeah, I would say that, these things that are in your mind, the mind is purely physical in my
Mm,
view.
mm,
So all of the representations that you have in your mind are, physical, say like dynamics of neural clusters, perhaps representations that can and do interact with the world
mm,
via your body and
mm,
via your language and all that sort of stuff.
mm,
So, it's like a single bit in a computer placed in the right place can destroy an entire infrastructure,
mm.
So it's like there's a whole branch of mathematics called catastrophe theory
Okay.
where, sometimes like the tiniest piece of like an atom, a single atom. I think I read a paper recently, a single atom that can cause a tornado.
Mm.
So like sort of the ultimate version of the butterfly effect.
Wow. Go down to
Um,
Adam even.
yeah,
Mm,
yeah. So it has to be perfect situations for that to occur. And usually it takes a whole storm to cause a tornado, but in the right moments, like a single, like smallest unit of matter can cause large scale changes.
mm.
And so if the mind is purely physical, doesn't matter how small these representations are, how weak they are
Or
in
even the
terms of,
fact that it's just a representation.
yeah, that representation, the cascade of the effects of that representation cause skyscrapers to emerge. So the cascade of the effect of Pythagorean's theorem is the understanding of put this brick on top of this brick, put this brick on top of the other brick, and you keep going, and then you end up with maybe not a skyscraper with bricks, but a tower. And yeah, so this idea, which is a physical idea, caused the consistent building of a tower.
Mm,
Um, so it's all very physical. I don't think
mm,
there's any barrier between mental and physical.
mm.
Um,
So you mentioned before we went back to that the idea of randomness and its origins as potentially being a purely uh, yeah. Or let me try to pose the question. Um, could you say that randomness disappears if you have a good enough representation of reality, and you just replace the concept of random events happening with just computationally bounded ability to predict the future?
Maybe. I guess if we were to restrict ourselves to like a classical view,
Mm-hmm.
then yeah, then perhaps if you have enough data
Mm,
about the system, you can remove randomness.
mm,
But I'm not so sure that that's how the universe actually does work.
mm.
So it's possible. Uh, yeah, right. So yeah, I don't know. I don't know.
What is your main sort of like mathematical concepts that you're playing with at the moment and developing? And of those concepts, what is the most interesting and intriguing one that you've come across so far?
Yeah, so right. Uh the So the idea that I'm trying to capture in my thesis, and to an extent I have, but it's a toy model, not like, what I think is the best way to do this. But I have this toy model for this ontological step that
Mm-hmm.
I was mentioning before,
Mm,
where what we do is we take a mathematical structure that we are trying to study, and we provide to it a context by which that context adds expressibility to the thing that you're trying to study. So the way that I have set this up is related to like Yoneda structures
Mm-hmm.
in category theory. So in category theory, there's a lemma that we like love to go back to all the time called the Yoneda lemma. And there's many different views on the Yoneda lemma, but the way that I see the Yoneda lemma is in terms of structural specification.
Mm-hmm.
So if I want to define a mathematical structure, I would create like a category which houses the axioms of that structure,
Mm-hmm.
and then the presheaves, so these say instantiations of these axioms
Mm-hmm.
are the actual structures. So you
Mm-hmm.
could think of it a lot like in like Python for,
Mm-hmm.
if you or in any programming language,
Mm-hmm.
you write down the definition of an object and then you can instance that definition.
Mm-hmm.
So there's the definition, and then there's the instances of the definition. And the Unida lemma gives you a handle on the instances of the definition if you have the definition.
Mm-hmm.
Uh, so, if you want to, for example, with a graph, access the edges of that graph. So the axioms are that a graph has nodes and edges, and there's an interaction between the nodes and edges. The instances are all graphs,
Mm-hmm.
and the Unida lemma allows you to access the nodes or the edges of that graph.
Okay.
Uh, so Unida structures are like a formal categorical abstraction of the Unida lemma.
Ah,
Because so the Unida lemma only works for one-dimensional categories,
interesting.
but categories themselves are mathematical structures. So there needs to
Mm-hmm.
be something that houses categories. And
Mm-hmm.
there's some paradoxes that occur, and also there's some structure that is missed if you try to fit the categories into like a category of all categories. So instead, you fit categories into like a a
Mm-hmm.
two-dimensional category
Mm-hmm.
of all categories. And that two-dimensional category, if you're generalizing the category of categories, has something called a Yoneda structure.
Mm-hmm.
So so if you want something that looks like a category,
Mm-hmm.
what you're looking for is an object of a Yoneda structure. So an object of the Yoneda structure of categories is a category,
Mm-hmm.
but an object of the Yoneda structure of fibered categories or monoidal categories or
Mm-hmm.
other highly structured categories are those different categories.
Mm-hmm.
So
And are you saying that those different categories you just mentioned are various instantiations with which the innate lemma would be able to reason about all of them?
these are different situations of the Yoneda lemma. So
Okay.
the,
Oh, of the
the
innate lemma itself. Okay.
So a Unida structure in general, like the class of Unida structures, would be able to reason about all these different types of categories.
Mm-hmm. Mm-hmm.
But a specific Unida structure knows how to argue about its specific type of category.
Okay. Okay. Mm.
So Yoneda structures were, used by, I think this was Ross Street and another author, but I forgot the other author. And so there was a period of time where people were playing around with these ideas. And, this guy named Wood came up with an idea called a pro arrow equipment. And, it wasn't so great, but finally, uh, a number of people, and it crystallized with Mike Schulman, and Geoff Crutwell was his co-author, wrote this paper on a unified approach to multi-categories.
Mm-hmm.
And in this paper, they define and quite simply define something called a virtual equipment.
Okay.
So a virtual equipment is like a Yoneda structure.
Mm-hmm.
The things inside of a virtual equipment you can consider to be categories.
Mm.
So it is like a meta theory of categories.
Interesting.
So let me just tie this all together for the viewer,
Yeah.
because that was a bit of meander through like highly abstract language.
Mm,
So categories are a meta theory for mathematical structure.
mm,
Virtual equipments are a meta theory for categories.
mm.
That's like maybe the slogan that is a bit easier to digest. I don't know.
And just thinking in terms of competing mathematical, well, I wouldn't even say maybe they're competing, but different kind of like mathematical theories. It sounds like what's happening there is kind of like what type theory was trying to solve for.
Hmm.
Maybe you can just like differentiate how type theory is not able to help with that, and or what the difference is like. What, and could you just apply like dependent type theory onto these categories to solve for reasoning about the structures
Yeah.
themselves?
So in the last 10, 20 years, there's been a real bridge between type theories and category theories.
Okay.
So um, there's a type of type theory
Mm-hmm.
called Martin-Loaf type theory.
Okay.
And this, like, these type theories are associated to different kinds of categories, different special kinds of categories.
Hmm.
So the dependent type theories are associated to locally Cartesian closed categories.
Hmm.
Uh, there's a direct correlation between the two.
Hmm.
Uh, Homotopy type theories, and this is a recent result, again by Mike Schulman,
Hmm.
are directly associated to infinity topoi, which are a type of category.
Hmm.
Um, so
Hmm.
so there's a interplay that is very deep
Hmm.
between category theory and type theory that is starting to become like really, really well recorded and
Interesting.
maybe easy to understand, whereas before it was impossible to understand the relation.
Maybe
Um,
just from a human perspective, can you explain what made it difficult and why is it easy now? Like when you say it's impossible, was it just too complicated? Like, or wasn't enough work done on it to like create the structures with which to say, oh, okay, it's obvious in hindsight.
so I'm new to type theory.
Mm,
So I don't actually know the history of
mm,
this. But like what I do know is Voevodsky is this guy who basically started the homotopy type theory univalent foundations program,
mm,
and he tragically died before being able to work on this more, but people have been carrying out his work. Um, and I think that, him and like guys like Steve Audi and others, were trying to like, so type theories are things that you can type. They're things that you can write into a computer.
mm,
There's like Lean and
mm,
Agda
mm.
and like plenty of different programming languages that are type theory programming languages.
TypeScript? No, I'm joking.
TypeScript. Yeah, no, I think so. I think so. Yeah, although I'm not so well versed with that one. But
What's interesting about
so
TypeScript is that
yeah.
divergence there is that they figured out that the types of type theory is Turing complete itself, which is kind of interesting.
Yeah. 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 I
I
mean
mean,
that makes sense.
there's something interesting to say about there is that just trying to apply type like structure to something on top of what was JavaScript, just trying to apply types to everything is so complicated and so complex that it actually is its own computer. And maybe that speaks to the power of type theory, maybe.
Yeah. Yeah.
Mm,
No, no, absolutely. So I mean maybe we'll just end on this because I think we can talk like infinitely. But like, and this is wonderful. Like we got to talk again.
mm,
And I'm sure we will.
mm,
So, you know, uh type theory is stuff that you can type into a computer.
mm,
Um, Category theory is all mathematical structures.
mm,
So the relation between type theory and category theory is, can we type all mathematical structures into a computer?
mm. Very
And so
interesting.
that's hard, but it's possible.
Hmm.
So
Okay. Last quick question from my side, and
yes,
this will be a quick hit from my side. Can you explain to me, please, what a monoid is?
a monoid.
Hmm.
Uh yeah, I mean, th oh man. So like there's quite a basic answer to this. A monoid is a set where you can multiply elements. So it's not necessarily that you can that the multiplication has an inverse or the multiplication I think maybe it does have an identity. So
Mm-hmm.
a monoid has an identity that you can multiply by. It has associativity,
Mm-hmm.
meaning you can put parentheses around things, but it doesn't necessarily have an inverse.
Hmm.
So monoids are like multiplication, like sort of the most basic version of multiplication on a set. Um, there is a deeper answer to this question, but I don't know. Like, what was the purpose of asking this?
A lot of people uh, that came across the concepts of monoids, it's almost a meme at this point. It's like no one understands a monoid. It's like no one understands quantum mechanics or no one understands XYZ. It's like
Oh, really?
uh,
I haven't seen that one.
yeah,
Um,
it's not a legitimate meme. Maybe I can start it, but every time you hear somebody trying to explain what a monoid is, it's almost like everybody gives a different answer, and that's why
yeah.
everyone's like, okay, well, if everyone's saying something different, what's going on here?
So I don't want to get too crazy with this concept, but it is something that I think about a lot, and it's a concept that John Baez brought up, and I think that
Hmm.
your viewers can go down a great rabbit hole with this
Okay.
concept.
Okay.
It's called the microcosm principle.
Okay.
And so the idea is in order to define a monoid, you need a notion of monoid in your meta theory. So to define a monoid, you need to already know what a monoid is.
Oh, I like
Um,
that.
so maybe this is what is going on in whatever meme space you're part of, but um, I mean,
Because it
there's
has
a
to do
very
with an
simple,
identity, right? It has to do with
yeah.
it's very intertwined with the fact that in category three, like some people say the identity is the monoid, or maybe I'm misinterpreting that. No,
No,
I misquoted that.
yeah, well, the endomorphisms of an object form a monoid.
Form a monoid. Okay. Okay.
Yeah.
Mm.
There's a notion of multiplication, a notion of identity,
Hmm.
but not necessarily a notion of inverse.
Interesting.
So, yeah.
Okay. Well, that's a very simple way of
Yeah.
thinking about it. So that's almost like the requirements for something to be monodal
Hmm.
is what you've just mentioned now. But then trying to explain like how monoids, like what you can do with monoids, or like what the benefits are, all that kind of stuff. That's where it gets maybe a lot more complex. Like
Yeah.
it feels like that's missing a lot of the information of what monoids actually are, what we described there. That feels like the requirements for monoid, but it doesn't feel like that's everything that monoids can do,
Hmm.
perhaps. Yeah.
Oh no, yeah, definitely not. Yeah, it's sort of like this principle that you were talking about with the universe. Like perhaps there's simple rules, but at scale, like
Mm,
there's so many different things. So
mm,
yeah, like I can define on paper what a monoid is, but I can't necessarily tell you everything you can do with it. So
yeah, makes sense.
yeah,
Okay, no, thanks so much for that. That was a great
yeah, thanks,
chat. What percentage of our topics did we manage to cover here?
man.
Does it feel like?
Almost 100%.
Okay,
Yeah.
great. Okay, well, we've definitely got resources to think about for the next session.
Mhm.
And the main thing I think, just as uh, a clue for what I'd like to get in for next time, is to start thinking about some of the stuff that we've reasoned about today and applying that to thinking about artificial intelligence specifically,
Right. We
and
didn't get to talk about AI. Yeah.
and also how, like how we mentioned, having these structures and these models and these mathematical concepts, how to reason about ourselves, potentially how to reason about intelligence as an abstract concept, and
Mhm.
maybe using these concepts and these like thought technologies in how to think about what we're going to do in the future of a potentially super intelligence that exists within society, and how we can leverage these ideas like the sea slugs, leveraging sort of the ability to reason about things for its survival. How can we leverage the power of pure mathematics to make sure that we survive in an environment where maybe much smarter things are going to have more control than we do in the future. So that's a
Right. Well, fingers crossed. So hopefully we figure that one out.
okay,
Um, yeah, great. Thanks for having
cool.
me.
Okay, pleasure.